Hey guys, Buildzoid here from Actually Hardcore Overclocking, and today we're going to be taking a look at Gigabyte's take on the extremely ridiculous motherboard for the equally ridiculous CPU. Say hello to the Gigabyte C621 Aorus Xtreme, Gigabyte's take on what a overclocking LGA 36, well, this is much more workstation-y, but still, overclocked workstation, LGA 3647 motherboard should look like for the 28-core 3175X Xeon from Intel.
Before that, this video is brought to you by Thermal Grizzly and their high-end thermal compounds. Thermal Grizzly makes cryonaut paste for high thermal performance and conductivity without being electrically conductive, so you don't have to worry about shorting components. Cryonaut is particularly good for replacing stock GPU pastes, as cryonaut is a non-curing compound. Learn more at the link in the description below.
So then, let's just get right into it, right? So, board's going to be around $1,400. I'm not sure when it's going to be like hitting retail, but it is basically a little bit cheaper than the the ROG Dominus board that we looked at previously, well, arguably, like, it's different. It's different. So let's go over some of the differences. So the first thing, power inputs. Gigabyte has opted for a much less flexible power input setup. So you still have the split 12-volt power plane, so half the VCC and VRM runs off of this, and the other half runs off of that. And the thing is that by less flexible, what I'm talking about is that Gigabyte opted for dual 8-pin CPU power connectors for both halves of the VRM, whereas ASUS with the Dominus, they had an extra 6-pin PCIe power connector, so if you had like a 1600 watt power supply, which normally only comes with two 8-pin CPU power connectors, you could plug in your two 8-pins and you could plug in two 6-pins, and you'd be able to power the CPU with just one PSU. With this board, you have to, well, you pretty much have to use dual power supplies because most power supplies don't come with 4 CPU 8 pins. So yeah, Gigabyte has basically decided that, they're going to force you into a dual PSU setup if you're going to be running this at high levels of CPU power draw. Though, honestly, for most cooling setups, you're probably not going to be able to, like, you're very likely going to be cooling limited before your power connector limited. So you might still get away with a single PSU setup as long as you don't go too ridiculous on how you're cooling the CPU. So anyway, we do also get, of course, the dual 24 pins directly on the motherboard so that the PSU, the dual PSUs power up in sync, right? You plug in both and the motherboard starts both of them at the same time as a result. And so that's how the power delivery is taken care of, and I just dropped my pen. Anyway, moving on, we do get a reset switch, a power switch, dual post codes. I am not sure what they're doing with the second one, but either way, these are always super handy to have when troubleshooting. Also, this has RGB on it. I just want to point that out. There's RGB on this board. Like, I have no idea how that got on here, but there's RGB. Anyway, then we have a random USB port inside the, directly, like, inside the case, essentially. I mean, personally, on a test bench, I'd welcome that, but I'm not sure what the use case would be in, like, a workstation environment. Moving along, we also get a speaker on the board, which, most, most consumer boards, I guess. I wouldn't really consider this a consumer board. I mean, this is just ridiculous. But, so most consumer boards don't bother with those, like workstation boards generally do, so that's present. You get the color-coded front panel header, which I'm a fan of, clear CMOS jumper right above that. This makes it a lot easier to see what you're plugging into. The ones that aren't color-coded are just, well, it's not quite as clear, is it? Then we get a BIOS switch for the dual BIOS system. This is a Gigabyte motherboard. Of course, it has dual BIOS. There's very few Gigabyte motherboards that don't. So the main BIOS here is actually socketed, which is kind of different from what they normally do. And then the backup BIOS is soldered onto the board. So the cool thing is, if you brick this one and then also brick this one, you can probably just ask Gigabyte to send you a replacement main BIOS chip, and you're going to be fine. There's also LEDs for indicating which BIOS chip is active, and those are right there. And that kind of covers it. There's no, like, retry button, safe boot button, any of the sort of extreme overclocking features that we saw on the Dominus, because Gigabyte considers this a workstation board. And even then, like, extreme overclocking boards from Gigabyte, Well, no, like when they do an extreme overclocking board, it has it has actually generally more buttons than anybody else out there. But yeah, they're really treating this more as a workstation board, and that's why, of course, we have a ton of PCIe 16X slots. Now, they're not all electrically PCIe X16. I mean, we can kind of clearly see that's an X8, that's another X8, that's a X16. This looks like either an X4 or an X8 again. That's probably an X8, and that looks like... This should be an X16 just because it's the first one, but it might be an X8 as well. So, you know, tons of PCIe expansion options because it's meant for workstations. And to make sure that you don't melt your 24-pin power connector, they have dual PCIe 6 pins. If you, I don't know, maybe ran like you could technically rig up 7 RX 480s onto this, you know, with like riser cables. It'd be a pretty bad idea as far as I'm concerned, but you could still do it. It wouldn't also be very practical, but it is doable. So anyway, they do give you dual 6-pin PCIe power connectors to make sure that the 24-pin doesn't melt. I am not a fan of the location. Okay, just like lots of workstation boards do this, but putting these right there is just like, so like, what, you're going to run a cable like that, or you're going to be running a cable like that, or you're going to be, well, you're not going to be running it across the top edge of the board because the board's actually like taller than the actual mounting holes right there. So this isn't going to fit in like any cases at all. So yeah, like this thing violates all of the form factors. It's its own thing. Anyway, so yeah, I'm really not a fan of the location. I totally understand why they exist. I can even kind of understand, well, I can't understand why they put them there because it's not like this area of the motherboard is particularly crowded. I mean, this right here is downright empty. And, you know, like there was no, as far as I'm concerned, there was no reason to cram all the I/O down here, especially no reason for that thing, right? Like, what? Get rid of that. This is obviously not being used. So, you know, a better thought out option would have been to take these, you know, clear out this area a bit. You know, you could probably shift some of these things apart a bit and then move those down there. And that would have been a much, like, tidier layout to manage cable-wise. But anyway, they decided to stick it right there. And here's one of those things that, you know, is just more workstation about this board that, like, this didn't actually end up getting on the board. But you can see that there was originally plans for a baseboard management controller to actually be on this motherboard. So that's essentially like a server thing which allows you to manage the system remotely. And yeah, they decided that they're not actually going to bother with implementing that. So I mean, I'm not sure how much of a big deal it is to anyone. I don't know that you would actually like want to build a server with one of these. I mean, on a core. No, well, no, there are definitely use cases for like a high core count, high frequency server, but I kind of feel like if you really care about your single threaded performance, you're just going to buy a 9900K and build a server with that anyway. Because that's just going to, like, the issue with all of the Xeons and all of the chips above X2, like, above LGA 1151 is that they use a mesh interconnect, and it's really quite, like, compared to the ring interconnect that you get on, like, a 9900K, it's relatively high latency. It's, like, approaching, like, it's not anywhere near as bad as, like, AMD's Infinity Fabric on latency, but it's getting there. It's definitely worse than ring. And so if you had like a really, really, really single-threaded workload, I wouldn't use a mesh CPU for it just because mesh sucks. So for single-threaded workloads. So anyway, moving along, we can kind of see that Gigabyte's opted for more, like the actual rear I/O is actually kind of bare. There's not much here, which is, again, I think the logic being that, you know, it's a workstation board. If you want USB ports, Ethernet ports, whatever ports, you got PCIe. Use it. So yeah, that's kind of what we can see going on in the I/O section there, and that pretty much covers it. There's not really much, you know, random junk just added onto this board because this really, like, Gigabyte understands that nobody's get like the couple people on Earth who are going to buy this anyway are probably not going to be like they're not going to use Wi-Fi, like onboard Wi-Fi or something. So Gigabyte hasn't bothered with anything like that. Though for some reason they did stick RGB on there. I never going to wrap my head around that. But before we get onto the voltage regulators, check out this heatsink. I'm a fan of this heatsink. Now, it's, you know, there's no fans in it, so Gigabyte has opted for a completely passive design. It is one giant block of aluminum, and this board's got to be so damn heavy. Like, seriously, like, this is one hell of an aluminum block. Like, yeah, so... Anyway, I am actually a fan of like this cooling design, and I think if it actually manages to maintain, like it should manage to maintain the VRM completely adequate thermally with this kind of design, because this heatsink's so damn big, the gaps between the fins are actually quite large. So it's not like they're super airflow restrictive. Like really dense fin stacks are actually kind of like they prevent airflow within them. So yeah, this should do a stellar job of cooling the VRM, and worst case scenario, it's just going to take forever for this to overheat because of how freaking heavy it is. Aluminum is actually not that bad in terms of its thermal capacity. So it just gets mixed up because it's real, like, you know, everybody thinks, oh, it's so light, it doesn't have a ton of thermal capacity. Well, no, relative to its mass, it actually has a really high thermal capacity per unit mass, but it's just a lot lighter. So it is still like a solid block of copper is still better than a solid, like, equally sized block of aluminum, but it's not that big a difference as you would expect just based on the weight. Anyway, let's go back to the voltage regulators. And well, I mean, there's a lot of them around the board, but obviously everybody just mostly cares about this great big strip of power. we shall call it that. So that right there is the VCC in. And unlike ASUS, where, you know, with the Dominus we had a lot of power stages and not a lot of phases, here we have a lot of power stages and equally many phases. This is a 32 phase. We will not be counting that, but we will be counting the quadruplers that this uses. And I give up on fixing GIMP. So the quadruplers are 1, 2, 3, 4, 5, 6, 7, and 8 over here. So that's how we get our 32 phases. Each of these essentially takes in one PWM signal and splits it into 4. In the process, they cut down the switching frequency to 1/4, which is actually a good thing for your efficiency because you're ultimately interleaving all of these anyway. So like one of the trade-offs between voltage regulator switching frequency and phase, well, it's like more switching frequency means less power efficiency. Okay, generally you're going to lose power efficiency as you crank up your switching frequency, but the benefit of that is you get better output ripple. Now, another way to get better output ripple is to interleave a bunch of phases, because if you have a whole bunch of phases interleaving, they'll actually sort of fill in the gaps between the, well, whatever. It's too complicated, I'm not going to describe that in this video, but essentially interleaving phases helps with your having a bunch of phases helps with your output ripple. So this does have a ton of freaking phases, and then it cuts down the switching frequency going through the doubler, so you actually can get the sort of the best of both worlds, where you have really good output ripple and really good efficiency at the same time. Now, the one downside to doublers is that they put a little bit of delay onto your PWM signals. It's generally sort of 10 to 20 nanoseconds, depending on what kind of signal you're trying to actually transmit. So that's something to keep in mind, and that can lead to, you know, it essentially means that your transient response can potentially be more, like, it can make it much harder to optimize it for whatever target goals you may have for your transient response. Anyway, so Gigabyte is using the 3599s here, and they are using 8 of them, so we do end up with a 32 phase VCC in VRM. It is controlled by this chip right over here in the middle of the board, and I actually really like how it's located right here. And we can actually see the 8 current sense inputs, so like 1, 2, 3, 4, 5, 6, 7, 8. And so this is one of like the issue. Well, this is an issue with any kind of multi-phase, like double design or quadruple design. The actual controller itself does not see individual phases. Doesn't see every single one of the phases. It essentially still sees this as a giant blob of 8 phases. And the controller here is, I am not going to put that on there. Nobody's going to be able to read that. Is, of course, the IR35201 that we find on basically every modern motherboard ever these days. Like, the only other chip you're ever going to, probably, like, high-end boards, only other chip you're ever going to see is, like, an ISL 69138. 138? 69? Yeah, 69138. Anyway, this goes up to 2 megahertz switching frequency, though I really doubt that's what they're actually running this VRM at. So I'm going with the operating frequency for this voltage regulator, like this VRM, to be at most at 1.6 megahertz on the controller, which would translate about 400 kilohertz on each of the phases. And that is running in 8+0 phase configuration. The chip can also run in things like 6+2 and anything sort of below those two options. So also a 7+1. So the actual power stages used in each of the phases are Gigabyte's favorite highlight. Well, yeah, they do use these a lot. So IR3556s. These are 50 amp power IR stages. So, you know, power stages from international rectifier. So that's why they replaced the ER with IR. Essentially, like, they're not as so on the Dominus we saw 70 amp smart power stages, also from well, Infineon at this point, those are basically a bit better at well, those are a bit smarter than power IR stages, but these aren't exactly dumb. So they still integrate current monitoring, they still integrate temperature monitoring, they just don't have some of the same safeties, and the current monitoring isn't quite as accurate as it is on the smart power stages. So yeah, that's the power stage that Gigabyte opted for. And so the resulting efficiency for this 32-phase monstrosity is for, well, we're going to be going with 1.8 volts output. So that's our standard output voltage for all integrated voltage regulator-based CPUs, like the Xeon 3175X. 400 kilohertz switching frequency, because that's just where the datasheet is spec'd at, so that makes my life easier, and also it's actually like kind of on the upper limits of what you would realistically want to run this at anyway. It's quite possible that this board actually runs at like 200 kilohertz on each phase, which like sets the switching losses for each of the phases. And then 5 volts drive, because while the 3556s do actually get more efficient at higher drive voltages, they are actually they're not necessarily built to like last as long at the higher drive voltages, and it's much more convenient to just grab 5 volts off of your 24 pin than messing around with building like a 7 volt or a 6 volt voltage regulator just to power the VRM. So anyway, the efficiency results. Well, this is kind of interesting. So for 270 watts at 150 amps output, this voltage regulator will produce about 21 watts of heat, which is ever so slightly worse than what we were looking at on the Dominus. But then at higher outputs, it actually gets a little bit ahead. And I think this is mostly down to the fact that the scaling for all of these operating parameters isn't optimal at low current outputs, but like... Anyway, like the error is not going to be huge, so very small advantage. Well, small disadvantage compared to the Dominus. There, the Dominus would be doing about 19 watts. Once we get into the efficiency curve of these 3556 power stages properly, which starts up at, well, I mean, we don't really get into the power, like the peak of the power efficiency curve is a long way away, but still, like at very low loads, power stages just have issues. And that's one of the smart advantages actually that the smart power stages have. At very low loads, they are slightly more efficient than all of the modern, than the older POW IR stages that we have here, which you can actually see right there, because this is just way too little current. You essentially, like, you wouldn't need a VRM heatsink on that at all. At this kind of current output. So anyway, moving on to something a bit more reasonable, 540 watts. This is usually where at least for like other platforms, say X299, this is around where your water cooling is just going to not be able to keep up anymore. Though I have heard that apparently it's possible to cool more on LGA 3647, which might be just down to the die being so much larger. But anyway, so 540 watts, which would be at 300 amps output, you're going to be looking at about 32 watts of heat output, which is a small advantage in favor for this board over the Dominus. So the Dominus would have been doing about 35 watts. Now, admittedly, these these aren't super accurate, so I honestly consider these pretty much equal anyway. Yeah, it's interesting how basically, 50 amp power stages don't, like, you'd think there'd be a bigger difference, but at these low loads, it's just kind of like, well, they're within margin of error because we're far out of the sort of the peak of the efficiency curve. And really, like, the Dominus will start to pull away the more current you start push through it. But with this many damn phases, like, you need a lot of current to start making a difference. Anyway, moving up to 810 watts, which, like, that's going to be really, really hard to cool if it's even possible. I'm not sure. But 810 watts and not 600. I'm misreading my notes. 450 amps output. You're going to be looking at about 45 watts of heat dissipation on the VRM. And at that point, the heatsink might start becoming somewhat useful, though I still think this would probably... Like, it might not run at a great temperature, but it would probably still not run at over 125 degrees Celsius at that point. So that would still be relatively tolerable to just kind of run without any kind of heatsink on there. Anyway, going yet higher, 1,080 watts of CPU power consumption, pushing 600 amps through the VRM. You're going to be looking at about 58 watts of heat, and at this point, you might want to, the heatsink might be a good idea at this point. And then 1,350 watts of heat. You're going to be looking at about 750 amps. And so CPU power consumption, 1,350 watts, 750 amps, and about 77 watts of heat on the VRM, which is still, funnily enough, like even now, this still has a small advantage over the voltage regulator on the Dominus. Which is basically a combination, as far as I'm concerned, it's a combination of the relatively low switching frequency and the fact that these are 50 amp power stages and that the efficiency curve, like we're still not really, past, like, we're still, like, the efficiency curve is just messed up, is not working out in favor of these voltage regulators with this many phases. I think this might be at the peak for these. So past this, the Dominus would start winning, though it is worth noting that in Der Bauer did a video with overclocking the 3175X on LN2, and he topped out at only around 1,225 watts on the actual, on the 8 pins. So he never managed to get over 1,200 watts. And this right here would actually be, because this is output power, this isn't input power. So this would actually be like 14 and, what is that? That's like 1427 watts on the 8-pin power connectors right there. So, yeah, this board is like, it's slightly less ridiculous overkill, but it's still ridiculous overkill. And bit better balanced in my opinion, and also it's nice that it's like $400 cheaper. I guess that's maybe a thing worth considering. Anyway, it's just like, it's a silly platform with silly motherboards, silly voltage regulators, and silly price points. So the end result is just, yeah, it's ridiculous. And I'm like, so far, none of the boards I've seen for the, like, unfortunately, there's basically 3 boards that I'm aware of that will be for this platform, which is like this one, the Dominus, and then the one that EVGA is working on. And I think at this point, EVGA is probably going to be the one bringing the reasonable voltage regulator. This is not one of them. This is a slightly less ridiculous thing compared to the Dominus, but still, it's just massive overkill. So, yeah, I mean, you know, well, I'm not surprised after the Dominus. That's where I'll leave it. Anyway, moving on to the minor rails, here we have what I assume is VCCSA, just because this location kind of makes sense for that rail. That's on just a 3553, which is the Gigabyte favorite 40 amp smart 40 amp power stage, not smart. So it's the same product line as the 3556. It's just a smaller package. It's cheaper, not by much, mind you. Yeah, Gigabyte uses that on like a ton of motherboards. Like they seem to have way too many of those because they're everywhere. Yeah, so the 40 amp power IR stage is right there. And for the controller, we're looking at an IR35204. So this is one of the other things that Gigabyte has done compared to the Dominus. Like, remember in the Dominus video, I was like, yeah, ASUS just smacked an ASP1405 on like literally every single rail they could find, which makes very little sense because the ASP1405 is like an 8-phase voltage controller. And so ASUS was essentially wasting these 8-phase voltage controllers on like single-phase rails. Well, Gigabyte has enough sense to actually go buy a different chip that isn't another IR35201. So if this was done like the Dominus, we would see that chip right there, and here, and here, and also there. Like, all of those would be more 35201s. But Gigabyte decided, you know what, that's just silly. So they actually opted for 35204s, and the 35204 is essentially a 4-phase variant of the 35201. Is it 4-phase? Yeah, it's 4-phase, or 3. I can't remember right now how many phases. It goes up to 4. It totally goes up to 4. Anyway, it doesn't really matter because we're like not going to be hitting the limits of what it can control either way. But so they have a 35204 up there, and that one's just running in 1+0 configuration. This one over here is running in 3+0 and takes care of our VDDR rail, which is this 3-phase right here. Yet more 3553s, so just more of those from International Rectifier. Then down here we have what I assume is going to be, so this should be VPP, and that's some kind of fully integrated buck converter on there, and so that's its own thing. We have another rail like that over there, which is a VPP, and that's a supporting rail. It sits at 2.5 volts, and it's for the DDR4 memory. Anyway, so we have those. Then we have what I can only assume to be VCCIO over here, which is another 3553 and a 35204. And then we have these two regulators, which I honestly don't know what those do. And then regulators over here, which I also don't know what those do. Something has to be powering the chipset, which could potentially also be that. And there's going to be just minor rails all over the place. But without having the board in hand, it's like, well, without having the board in hand, or at least like an Intel platform specification, which I didn't manage to find, yeah, it's really hard to tell what any of those are. But there's a bunch of minor rails all over the board, and those just use yet more International Rectifier parts. I wouldn't worry about them. You're probably never gonna, like, you'd never, on the off chance that the BIOS gives you control over them, you'd never want to change them anyway, because they don't do anything. Like, it's bad if they stop working, but there's no point messing with them 90% of the time. Anyway, VDDR over here is yet another 3-phase. So, controlled by yet another 35204. So that covers it. Gigabyte's take on the extremely ridiculous motherboard for the equally ridiculous CPU. Admittedly, Gigabyte's extremely ridiculous motherboard is like ever so slightly less ridiculous than the ASUS one. It's also ever so slightly less less expensive. I mean, $1,400 versus $1,800. Well, it's not like it's going to fund a new Titan. Like, you're probably going to be running Titan RTXs on something like this anyway. So at that point, it's just like, eh. I guess you could put the money towards more water cooling, because you'll probably need it for the CPU if you plan to do any serious overclocking. So, yeah, that's it for the video. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support Gamers Nexus, well, there's no mod mat on the screen right now, but there's store.gamersnexus.net for any sort of like shirts, mod mats, and other merch you'd like to buy. There's also the Gamers Nexus Patreon if you'd like to support us directly. And I have a channel called Actually Hardcore Overclocking where I do other overclocking related content. So that's it for the video. Thanks for watching and goodbye.